Welcome to the lecture on matrices and determinants. In the last lecture we introduced the notion of a matrix and we saw some properties of the matrices, especially we saw how to add matrices. Now let us look at the second one, what is known as scalar multiplication. So we are going to multiply a real or complex matrix by a real scalar or a complex scalar. Let A be an n by m matrix, that is I have A as Aij, where I runs from 1 to n and j runs from 1 to m, and let alpha belong to R set of real numbers or C, right. So, by an n by n matrix the entries are just real number or a complex number. So, we define the matrix alpha dot A as follows. So, alpha dot A, its ijth entry is given by alpha times Aij, right. So, thus the matrix alpha dot A is given by alpha times Aij. So, once you have this definition, now let us look at some of the properties of this scalar multiplication. First one that you can notice is that if you have alpha and beta are any two scalars, then alpha plus beta, if you multiply it on A, this is same as alpha dot A and beta dot A, and then add these two matrices. Now, how to do this? How to give a proof of this? So, now let us write down alpha plus beta dot A. Well, so solution or a proof. So, because you have the matrix, let me write the matrix A as Aij, then by definition alpha plus beta dot A, this is going to be alpha plus beta dot Aij, but we know that addition and multiplication they are distributive for real numbers. So, this is same as alpha dot Aij plus beta dot Aij, and this is same as by the definition of addition of matrices alpha dot Aij, this matrix plus the matrix beta dot Aij. Now, again by the definition of the scalar multiplication, this is same as alpha dot Aij plus beta dot Aij, which is equal to alpha dot A plus beta dot E. Second one, for any scalar alpha and for any two matrices A and B of same order, alpha dot A plus B is same as alpha dot A plus alpha dot B. So, you are given that A and B are of same order. So, let me write A as Aij and B as Bij, where A and B, the matrices A and B are of same order. So, alpha dot A plus B, which is same as alpha dot, let me write down in terms of entries. so that things will be, so let me use a small letter, so that things will be much clear. Alpha dot Aij plus Bij, by definition of the matrix addition, right, the entry wise you add them. So, it is going to give you the matrix Aij plus Bij. Now, by the definition of the scalar multiplication, this is going to just give you alpha dot Aij plus Bij. Again use the fact that addition and scalar multiplication, they are distributive, therefore, this is same as alpha dot Aij plus alpha dot Bij. So, one thing that you will have to notice in the second thing is that second equality, that this holds because of the fact that A and B are of same order, therefore, you can add them, right. So, having said all these things, we have finally come to the place where we have alpha dot Aij plus alpha dot Bij as the ijth entry. By the definition of the addition of matrices, this is same as alpha dot Aij plus alpha dot Bij. Again let us use the definition of scalar multiplication. This is same as alpha dot Aij, the matrix Aij plus alpha dot the matrix Bij. So, this matrix is with entries Aij, this is exactly alpha dot A plus alpha dot B. Third one, alpha dot beta for any two scalars A alpha and beta, alpha dot beta dot A is same as alpha dot beta dot A, which is same as beta dot alpha dot A. Well, it is enough to prove one of these things. So, first and second, because the third one follows because alpha dot B is same as beta dot alpha. So, alpha dot beta dot A. So, as usual we assume that A is of the form Aij, which is say alpha dot beta dot Aij. Alpha beta, it is again a scalar. So, you are multiplying with the matrix A. So, by definition this is same as the matrix whose entries are multiplied by the scalar alpha beta dot Aij. Notice the fact that the multiplication of scalars is associative. So, this is same as alpha dot beta dot Aij, which is same as alpha times beta dot Aij, right. You have alpha times beta dot Aij, which is equal to alpha times the matrix beta dot Aij, but then the matrix within the bracket is exactly beta dot Aij is equal to alpha dot beta dot A. So, these are some of the properties of the scalar multiplication. There is one more operation on the set of matrices, is what is known as transpose of a matrix. If A is any matrix, then the transpose of A denoted A transpose, this T means transpose, is obtained obtained as follows. Right, how do you obtain? So, let me write A as Aij and let B equal to, or let me write A transpose this matrix as the entries as Bij. So, then Bij, what are these? This is given by Aj. These are given by Aj. This is the definition of the transpose. So, once you have the transpose, so if A is a matrix of order n by m, then the transpose A transpose is a matrix of order m by n. You will have the other way m by n. Well, let us try to do an example. Let us try to calculate the transpose for some of the matrices. First one, let A equal to 1 by 2, 1 by root 2, 1 by root 3, 3, 1 by root 3, 1 by root 5, 5, 1 by root 5, 1 by root 7. Now, let us try to calculate A transpose. Ijth entry of this is the jith entry of the corresponding matrix A or the underlying matrix A. So, the first one 1/1th position. So, we will have to look at again the 1/1th position, it is half. Second one what you have is 1/2th position. So, you will have to look at the corresponding entry in the 2/1th position, which is 3. Again you have 1/3 position. So, you will have to pick the element from the 3/1th position, which is 5. Again you have, so this is the 2/1th position. So, you will have to look at the 1/2th position, which is 1 by root 2, 2/2th position 1 by root 3, 2/3th position. So, look at the 3/2th position, which is 1 by root 5. Again this is 3/1th position. So, look at 1/3th position in the corresponding matrix A, you have 1 by root 3, 1 by root 5 and then finally 1 by root 7. Right. This is the transpose of the matrix A. Let us do one more example. Let us write down a matrix with a complex entries, with some complex entries I. So, where I denotes the complex number 2i, 1 plus 2i, 3i, 2i, 1, 2 plus 3i, 4 plus 5i, 3, 4. This is the matrix. Now, let us try to calculate A transpose. First one, it is exactly same as I. Second one, the 1/2th position. So, you will have to look at the corresponding entry in the 2/1th position, which is 3i. Now, let me just write down, this is 4 plus 5i. So, the first column will be converted here as first row. So, what you need is a second row. So, you will have to look at the corresponding second column. So, 2i, 2i, 3. Now, I want the last row. So, you will have to look at the corresponding last column, 1 plus 2i, 2 plus 3i, 4. So, this is the matrix that we have. Now, let us look at some simple properties of transpose. First one, if you have two matrices of same order, then A plus B whole transpose is equal to A transpose plus B transpose. Proof: A plus B whole transpose. So, let me write A as Aij and B as Bij. So, now A plus B, this makes sense only if A and B have got the same order, and so what you will have to, as mentioned earlier, what you will have to assume is that A and B should have the same order. So, what we wanted is A plus B whole transpose, which is same as Aij plus Bij whole transpose, which is equal to this matrix Aij plus Bij the whole transpose. So, once you, when you take the transpose, ijth entry goes into jith entry and the element in the jth position goes to ijth position. So, what you will have when you take the transpose, you will end up with Aj plus Bji, which is same as, by the definition of matrix addition, this is same as the matrix consisting of Aj's plus the matrix consisting of Bji's, but this is same as A transpose and the next one corresponds to B transpose. Therefore, A plus B whole transpose is equal to A transpose plus B transpose. Second one, for any scalar alpha and any matrix A, alpha A whole transpose is same as alpha times A transpose. Proof. So, as usual, let me write A as Aij, then I wanted alpha times A whole transpose, which by definition is alpha times the matrix with the entry is Aij whole transpose, which is same as alpha times Aij the whole transpose. So, the ijth entry is given of this is given by alpha times Aij. I need the transpose of this. So, this is going to be the matrix with entries alpha times Aj, which is equal to this, when I same as my definition of matrix scalar multiplication with a matrix alpha times Aj, which is same as alpha times A transpose, right. Thus, we have what we wanted. Fine. Let me go to the next definition. A matrix A is called a symmetric matrix if A equal to A transpose. Similarly, a matrix A transpose, sorry, matrix A is called a skew symmetric matrix if A equal to minus of A transpose. By minus of a matrix I mean minus 1 times of that matrix, right. Let us look at an example. Let us look at this one. A is 1, 2, 3, 2, 3, 4, 3, 4, 5. So, let us first try to calculate A transpose. So, 1, 2, 3, 2, 3, 4, 3, 4, 5. This is the one that we have obtained after taking the transpose. So, note that A equal to A transpose, therefore, A is symmetric. So, the next example, let A be an upper triangular matrix. So, what you have is an upper triangular matrix, then A cannot be symmetric unless A is a diagonal matrix. Right, for A to be symmetric, you want the ijth entry and the jith entry to be one and the same, and for an upper triangular matrix you know that all the entries below the diagonal should be 0, and therefore, which means for an upper triangular matrix to be a symmetric matrix, you want all the entries even above the diagonal should be 0, and that means that it should be a diagonal matrix. So, in particular, every diagonal matrix is skew symmetric. Now, let us do some more properties. Well, if A is any matrix, then I need a square matrix. Any square matrix, then A plus A transpose is also a symmetric matrix. Right. If A is any square matrix, then A plus A transpose is a symmetric matrix. Proof. How to prove this? So, let A equal to Aij, it is a square matrix, then A transpose, the entries are given by Aj. This is the ijth entry of A transpose is Aj. Fine. Now, let us try to calculate A plus A transpose. A plus A transpose is given by the matrix Aij plus the matrix Aji. Right. So, Aji means a matrix with entries, ijth entries as Aji. But this again by the definition of the addition of matrices, this is Aij plus Aji. Fine. This is what we have. Now, let us try to calculate the transpose of this A plus A transpose. which is the transpose of the matrix whose ijth entry is aij plus aji. If you have a matrix A with entries aij, then its entries, the entries of A transpose is given by aji. Now, I have a matrix whose ijth entries are aij plus aji, and therefore, I will have to just swap I and j. So, the entries are given by aji plus aij. Again note the fact that the addition of real numbers is commutative, and therefore, this is same as aij plus aji, which is same as A plus A transpose. So, let me call this as 1 from 1, right. Thus, what do we have? A plus A transpose, this matrix is symmetric. Fine. Similarly, if A is any square matrix, then A minus A transpose is a skew symmetric matrix. Proof: as usual, let A equal to the matrix aij, then the matrix A transpose is given by aji. So, once you have this, so as usual, let us start writing the matrix A plus A transpose. So, you have A plus A transpose. If you look at the previous ones, then this is going to be same as, so what we wanted is A minus A transpose. So, this is going to be aij minus the matrix aji, which is same as aij plus minus aji, which by definition of matrix addition is same as aij minus aji, right. So, let me call this as 1. I will have to look at the transpose of A minus A transpose, A minus A transpose, the whole transpose. It is the transpose of the matrix whose ijth entries are given by aij minus aji, aij minus aji whole transpose. Now, let us try to apply the definition of that transpose. This is same as minus aji plus aij, this is equal to minus of aij minus aji, which is same as minus of aij minus aji, which is equal to, and this matrix aij minus aji, this is exactly A minus A transpose. This follows from 1. Thus, A minus A transpose is a skew symmetric matrix. Now, let us do an important theorem in this direction. given any square matrix A, it can be written as a sum of a symmetric matrix and a skew symmetric matrix, right. So, given a square matrix, you can write it as a sum of a symmetric matrix and a skew symmetric matrix. The proof uses the fact that A plus A transpose is symmetric and A minus A transpose is skew symmetric. Well, so let A be any square matrix so the claim is that A equal to B plus C, where B is a symmetric matrix and C is a skew symmetric matrix, right. I should write A as B plus C, where B is a symmetric matrix and C is a skew symmetric matrix, fine. How to do that? So, let B equal to A plus A transpose and C equal to A minus A transpose. Then from what we have done previously, it follows that B is a symmetric matrix and C is a skew symmetric matrix. Now, the only thing that we will have to show is that B plus C is A, but this follows from the properties of the addition of matrices. Well, let us try to prove it. B plus C equal to B is A plus A transpose plus C is A minus A transpose. Well, what I need is whole upon 2. That means, I am just multiplying this matrix A plus A transpose by 2 and similarly A minus A transpose this matrix by 2, right. So, I need by 2. Now, by the properties of the scalar multiplication, we know that alpha times A plus B is alpha times A plus alpha times B. So, this is same as A by 2 plus A transpose upon 2 plus A by 2 minus A transpose upon 2. So, this is same as A by 2 plus A transpose, use the fact that it is associative. So, the order is immaterial plus A by 2 minus A transpose upon 2, right. So, by A by 2 it means that you are multiplying the scalar half with the matrix A, similarly for the other things, and you have A by 2 A transpose by 2 and minus of A transpose by 2. So, therefore, these two gets cancelled. What you have is A by 2 plus A by 2. Let us use the properties of the scalar multiplication. This is half plus half times the matrix A, which is 1 times A, which is just A. So, this is what we have. So, thus B plus C is A, or A equal to B plus C, where B is a symmetric matrix and C is a skew symmetric matrix. So, what have we done? We have returned a square matrix as a sum of a symmetric matrix and a skew symmetric matrix. Now, let us do one more thing of what is known as the multiplication of matrices. Earlier we saw about multiplying a scalar with a matrix. Now, let us do multiplication of matrices. We are going to multiply two matrices. So, here the order is very important one for multiplication, right. So, certain things are very important. So, let me just first state it. Let A be a matrix of order m by n and B be a matrix of order n by r, right. So, this n and this n. So, the number of columns in matrix A should be same as the number of rows in the matrix B. Then the product of A and B denoted AB is obtained as follows. So, as usual I will write A as Aij, where I runs between 1 to m and j runs between 1 to n. B I will write it as Bij, where I runs between 1 to n and j runs between 1 to r, and therefore, the matrix AB. So, let AB equal to C, let me write it as Cij. Then, so the ijth entry, that is the Cij, is given as follows: summation k running from 1 to n Aik Bk j, right. So, summation 1 to n Aik Bkj. Well, so now let us try to do one example. I have A as 1 2 3 4, B as 5 6, here m is 2, n is 2 and r is 1, and order of A is 2 by 2, order of B is 2 by 1, these two matches, and therefore, A and B can be multiplied. Fine. Therefore, 1 2 3 4 multiplied with 5 and 6, this is going to give me the first entry, summation 1 to 2 A I. So, I, the first entry is 1 k B k j, it is only 1. So, I have only one column. So, summation 1 to 2 A 2 k B k 1. because I have only one column for B, so only this much is there, fine. Let us try to expand things. This is going to give me A11 B11 plus A12 B21. Second one A21 B11 plus A22 B21. What is A11 B11? A11 is 1, B11 is 5 plus A12 plus B21 6. So, 6 into 2 12. Second one A21 3, B11 which is 5, 5 into 3 15 plus A22 4 into B21 which is 6 24. So, the final matrix that we have obtained is 17 and 39. This is the matrix that we have obtained. Let us do one more example. Let us do it for a 1, 2, 3, 4. This is your matrix A, and your matrix B is 1, 2, 3, 4, 5, 6. Let us try to calculate. Right. So, this is an 2 by 2 matrix. You have 2 rows and 2 columns, and this is a 2 by 3 matrix, and if you notice these two matches, and therefore, this is a these two are matrices which are compatible for multiplication, and therefore, AB, how do I multiply? If you look at the previous one, if you look at things, what is happening? You are multiplying the first row with the first this column, and similarly this thing with this one. So, first entry 1 with 5 and 2 and 6, that is what you have done, right, 1 with 5 and 2 with 6, 3 with 5 and 4 with 6. Let us do the same thing, that is what it says. So, 1 with 1 1 times plus 2 with 2 which is 4. Similarly, 1 with 3 with plus 2 with 4 which is 8, again 1 with 5 which is 5 plus 2 into 6 which is 12. Second row 3 into 1 which is 3 plus 4 into 2 which is 8, 3 into 3 which is 9 plus 4 into 4 which is 16, 3 into 5 which is 15 plus 4 into 6 which is 24. So, what is the final resulting matrix? 5, 11, 17, 11, 25 and 39. This is the one that you have. 5, 11, 17, 11, 25 and 39. Let us try to go a bit further and try to do a bit difficult example. Let us look at two matrices A with entries 1, 2, 3, 4, 5, 6 and 7, 8, 9, and a matrix B with entries 1, 2, 3, 4 and 5, 6. If you look at the matrix A has got order 3 by 3. If you look at the matrix B, it has got order 3 by 2. These two entries or these two things matches, right. This is of order m by n and this is of order n by k, and therefore, these two matches, this 3 and this 3 matches, and therefore, these two matrices A and B are compatible for multiplication, or they can be multiplied. Now, let us try to multiply A and B and find out what AB is. So, what we will have to do is multiply the first row with each of the columns till all the columns are exhausted. 1 into 1 which is 1, 2 into 3 which is 6 plus 6, 3 into 5 which is 15. Next one 1 into 2 which is 2 plus 2 into 4 which is 8 plus 6 into 3 which is 18. second one 4 into 1 4 plus 5 into 3 15 plus 6 into 5 which is 30, 4 into 2 8 plus 5 into 4 20 plus 6 into 6 36, 7 into 1 7 plus 8 into 3 24 plus 9 into 5 45. Last one 7 into 2 14 plus 8 into 4 32 plus 9 into 6 54. Let us write down the final one just by adding these. 6 plus 1 7, 7 plus 15 22, 2 plus 8 10, 10 plus 18 28, 4 plus 15 19, 19 plus 30 49, 20 plus 8 28, 28 plus 36 64, 7 plus 24 which is 31, 31 plus 45 which is 76, 14 plus 32 which is 46, 46 plus 54 which is 100. So, this is the final resulting matrix. Now, let us look at one property regarding matrix multiplication and transpose for any two square matrices A and B of same order AB whole transpose is equal to B transpose A transpose. Proof. As usual, let us write A as Aij and B as Bij, right, wherein 1 less than or equal to I comma j less than or equal to n, right. That means, we are assuming that A and B are of order n by n, and this is possible because it is given that A and B are of same order and they are square matrices. Now, let C equal to AB, let me write it as Cij. What does it mean by Cij? Where the ijth entry of the matrix C is given by summation k running from 1 to n Aik Bkj, right. This is what we have. Now, let us try to calculate AB whole transpose. What does this mean? We are looking at transpose of C, that means, we are looking at the matrix Cij and then taking the transpose of this, which is equal to Cij whole transpose Cij, which is going to give me the matrix with entries Cji. What are theseCij's? I know what Cij's are. So, let me just use it and then write down summation k running from 1 to n Ajk Bki, right. So, the matrix of AB whole transpose have got entries summation k equal to 1 to n Ajk Bki, these are the ijth entry. Once I have these, now let us try to calculate B transpose A transpose, which is equal to, look at the matrix with entries Bij, take its transpose. Similarly, look at the matrix with entries Aij, take its transpose, which means this will give me Bji, the other one will give me Aji. So, I have two matrices with entries with ijth entry as Bji and Aji respectively. I will have to multiply them. So, the resulting matrix is going to be summation k running from 1 to n. The ikth entry of this matrix Bki
and the other one I need the jkth entry, which is a k j, right. The first one b k I represents the I kth entry of the first matrix, and the second one a k j represents the j kth entry of the second matrix, which is equal to summation k running from 1 to n. Let me just rewrite this, which is a k j b k I, right. I have just used the fact that whether it is complex numbers or real numbers, they are, you know that they are commutative, multiplication is commutative, I have just used this. Now, if you look at what we calculated for A B whole transpose, these two matches, and therefore, this is same as A B whole transpose. Thus, A B whole transpose equal to B transpose A transpose. Now, let us do a simple example. Let us look at this matrix 1, 2, 3, 4, 5, 6. This is a matrix, let me call it as A. This is a matrix of order 2 by 3, and let me choose B as 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 4, 5. So, this the first one A, it is a matrix of order 2 by 3, and B, it is a matrix of order 3 by 4, and we know that the resulting matrix. So, these two numbers matches, therefore, they are compatible for multiplying, or they can be multiplied together. Therefore, the resulting matrix is 2 by 4 matrix, it is a 2 by 4 matrix. On the other hand, and therefore, it is a 2 by 4 matrix, therefore, let us try to calculate A B. 1 plus 10 plus 3, 2 plus 12 plus 6, 3 plus 14 plus 12, 4 plus 16 plus 15, next row 4 plus 25 plus 6, 8 plus 30 plus 12, 12 plus 35 plus 24, 16 plus 40 plus 30, which is equal to 11 plus 3 14, 29 plus 6 35, 14 plus 6 20, 38 plus 12 50, 17 plus 12 29, 47 plus 24 71, 20 plus 15 35, 56 plus 30 86, right. We have this as A B, and therefore, A B whole transpose, which is equal to I have. So, this is a matrix of order 2 by 4, which means the transpose will be of order 4 by 2, 14, 20, 29, 35, 35, 50, 71 and 86. I have this. Now, let us look at B transpose. B transpose, which is 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 4, 5. We know that B is a matrix of order 3 by 4, and therefore, B transpose, this is a matrix of order 4 by 3. On the other hand, A transpose, which is given by 1, 2, 3 and 4, 5, 6. This is a matrix of order 3 by 2, and therefore, so these two matches, they both are compatible for multiplying. Let us calculate B transpose A transpose. 1 5 1 2 6 2 3 7 4 4 8 5 into 1 4 2 5 3 6. Let us compute it, which is given by 1 plus 10 plus 3, 4 plus 20 plus 6, 3 plus 12 plus 6, 8 plus 30 plus 12, 3 plus 14 plus 12, 12 plus 35 plus 24, 4 plus 8 plus 15, 16 plus 13 plus 30, 16 plus 40, right, 4 plus 16, 4 plus 16 plus 15, 16 plus 40 plus 30, which will finally give me 14, 15 plus 6 21, 2 plus 12 plus, sorry, this should be 2, which will give me 20, this is 29, 35, 30, 4 plus 20 plus 6, sorry, this should be 25, this should be 25. So, this will give me 35 and then 38, this is 50, 47 plus 24, 71, 70, 86. One can notice through this example that AB whole transpose is equal to B transpose A transpose. I will stop here. In the next class we will see some more properties of matrices, and we will try to define the notion of what is known as invertibility of a matrix. Thank you.